Hi everybody, this is Mrs. Ewald signing in, and what I'm going to do is take you through a very quick lesson on an introduction to electrochemistry. So I will take you through more of the conceptual background about what electrochemistry is, and then Miss Heaton in her next podcast, which goes through the standard reduction potentials, will show you how we use these drawings of cells, voltaic cells or galvanic cells, and how we're able to then calculate voltage from it. So I'm going to just take you through a very quick intro of this. So why is it that we need to study electrochemistry? Well, you should remember, anytime you see electro, you should think electron. So we are going to be talking about the movement of electrons. Now, what have we already studied? Let's just recap. We have already studied redox reactions. And you should know that the purpose of a redox reaction is to be able to track the electrons. So if you have something lose an electron, there needs to be something there to catch that electron. So when you play a game of catch, you're going to be having someone throw the ball, and then somebody's going to have to catch the ball. Now, if you need further resources and learn more about electrochemistry, please make sure that you look in the book in sections 18.5 to 18.6. It will go through, very similar to what I'm going to be going through, what electrochemistry is and the types of batteries that you can have. So, the applications to electrochemistry. Now that we understand this reaction, we will see how this reaction is used in multiple ways. Batteries, for example, how we're able to harvest the energy, be able to get energy from that and have it to do work. That's one huge thing. Corrosion, understanding why things corrode. Not only why, but also we have to come up then with other ways of preventing corrosion, like in airplanes or big water vats, being able to prevent that. You also have industrial production of chemicals using electrochemistry, so the making of chlorine, sodium hydroxide, fluorine, aluminum. Again, these are all things that we need in our daily lives. And then you also have the biological redox reactions that occur. Remember, the hemi group, that is your blood. So understanding how you have the iron on your red blood cells, and understanding then that's how we're able to get oxygen and attach that. And you should maybe remember in biology, we actually talk about diseases that can occur with this. For example, hemochromatosis. That is a disease where a person actually has their organs rust inside of them. That is a redox reaction. It's pretty cool stuff. What is an electrochemical cell then? So this is an apparatus that is going to allow, again, the redox reaction, so going back to what we've already learned, and you should be able to visualize what that is, by transferring electrons through an external connector. Why do we want to use an external connector? Why? Because we want the electrons to move through a wire. And it is by having it those electrons move through a wire, that you have the electrons moving from low energy to high energy. That will produce a current, and that current will then allow the electrons to flow and can be directed through a device, or a motor, a light bulb, a fan, multiple different things that we need in order for it to do work. Now there are two different types. Let me move this down. There are two different types of electrochemical cells. We're first going to be dealing only with voltaic or galvanic cells. You may use either name. You could use it interchangeably. Those are product-favored reactions, meaning that they're spontaneously going to happen. And those are the types that we are going to be drawing first. You also have a reactant-favored, which is an electrolytic cell. What that means is it's going to require an electric current first in order to get it to cause a chemical change. So there are multiple different types that can happen. This is what you're going to need to be able to draw and be able to understand how all of this is functioning. This is a very simplistic way, if you were to kind of draw down the center here, of how a battery works. And so if you were to have just simply two beakers, you can make a battery. If you had a lemon or a lime, you can make a battery actually. But this here shows you how you need to separate the solutions and how you're going to divide it up into your anode and your cathode. So you need to, in your notes, be able to draw this. Think of this as one beaker, so beaker 1. This is beaker 2. In one beaker, you're going to have zinc ions. In the other beaker, you're going to have copper ions. You also need to have these two solutions connected, and this is what we call a U-tube. No, folks, it's not the same U-tube that you find on the computer, but it is in the shape of a U, and it does allow for the movement of the ions. That is what a salt bridge is, and helps to move the ions from one solution to the other. And we'll talk about the importance of that in a moment. You are also going to have your metals. So you're going to have a zinc metal on this end and a copper metal on this end. These then are going to have alligator clips and be connected through an outside wire. Why? Because this wire will allow the electrons to move through it. This then allows for this to be able to be hooked up to a light bulb, a fan, whatever it is we need to do work to allow this current, and then therefore allow work. So, over here you need to know the terminology. This is the anode, this is the negative end of the battery, and this over here on the right is the cathode, the positive end. You're always going to put the metal on the left if it is the anode. I typically always do anode cathode when I'm doing my drawings. Does it have to be that way? No, you could just flip it, it doesn't matter. But the anode, because this is the negative end of the battery, this means that zinc is what is being oxidized, because it is going to have to lose electrons. So the flow of the electrons is going to be from this end of the cell to this end. So the cathode then must be where reduction occurs. So this is where the electrons will go, and therefore copper is being reduced. So this is an overall very simplistic example, and you should be able to draw this, of what an electrochemical cell looks like. You're going to be required to draw it and then do calculations with it. Now, really quickly, just to backtrack, you've already done a redox lab where you're able to see in certain situations a chemical reaction will occur, and then in other situations it will not, because it actually requires an outside source of energy. So you know from your lab that you did just recently that when you placed your zinc metal inside your copper sulfate solution containing the copper plus 2 ions, the copper plated out onto the zinc metal strip. Now some of you may have been able to see that, some of you may have been not, but it does. And what you should have seen then is the zinc strip slowly will disappear. This is because the zinc is being oxidized inside that solution. It is losing electrons and is therefore the reducing agent. The copper plus 2 is being reduced and is the oxidizing agent. And so you're able to then be able to see the copper solid kind of plate out. If you looked very carefully, you might have been able to see that on the surface of the zinc. Now, this is just a precursor. Again, we're going to go back to this idea. So to obtain a useful current, we have to separate the oxidizing and the reducing agent. So you have your reducing agent here and your oxidizing agent here. So that the electron transfer can occur through this wire. Now we will take you through, both Miss Heaton and I, in class, this website where we'll actually be able to show you visually how this happens. So you can actually see how the zinc will lose mass because it is being oxidized, and how the copper will actually gain mass. Because as it's taking the electrons, the copper plus 2 takes those electrons to make more copper and is plated out onto the copper metal. And so we will again go through this in class together. So going back, what is it you need to know? Well, you need to know that the zinc is being oxidized. What is oxidized will appear at the anode, and this is the negative end of the battery. Again, typically we write it so that the anode is on the left and the cathode is on the right. Does it have to be that way? No, but you do want to make sure that you show the correct direction of the electrons. Electrons will always move from the anode end to the cathode end, so you could draw it like that, just showing the direction of your electron. The electrons are going to travel through the external wire, and then you also need to make sure you show the U-tube with the salt bridge. Now let's talk more a little bit too about the salt bridge in a bit. Over here is the copper. Copper is being reduced, it's taking the electrons to make more copper and plate that out onto your copper metal. This on the cathode end is where reduction is occurring. So this is the positive end of your battery. This is just a way of remembering red cat, reduction, cathode, in case that helps you. So the reduction is the cathode, it's the positive end. Now, if the electrons are moving from the anode to the cathode, eventually what will happen is that you're going to lose all of the electrons from this part of the cell and add it over to the right side. So this becomes very positive in a way, and this will then become very negative. Now this is going to be a bad thing because eventually it's just going to stop and it's just going to build up and you're going to have these opposite charges. The whole purpose of this battery is in order to get the electrons to keep flowing. We want to create a circuit so that the electrons keep going around and around. That's how we're going to get our harvesting our energy. And so this is where ions become very, very important. So the anions from over here then, these are going to need to travel through the salt bridge over to the left side. So always remember, anions will move over to the anode. A. Anions move to the anode. So those are your negative anions moving back over to replenish the negative charge that is lost over on this side. That helps in order to keep the net charge 0 and complete the circuit. If you have the negative moving over here, that will then help so that you keep the negative electrons moving in the circular flow. But then you also need to replenish the positive over on the right. So the cations that are made over on the left or in the salt bridge are going to be moving over to the right. Again, helping to keep the net charge 0 and complete the circuit. So that is really the purpose of the salt bridge, to keep your circuit, keep the electrons flowing, so that way you constantly have the electrons moving through the wire. Otherwise it just stops and it doesn't work. You have a dead battery. Now, the question is, how do we know what is being oxidized and what is being reduced? Going back really quickly, I told you that zinc was oxidized and I told you that copper was reduced. But how do I know that? Ms. Heaton is going to take you through in great detail the standard reduction potentials and how to calculate that. But what you need is the chart of standard reduction potentials, and this will actually tell you then by that table what is being oxidized and what is being reduced. So that way you know how to draw your cell and therefore calculate your voltage. So E to the naught, that is showing you your standard reduction potential, so your voltage in V. So how much energy are you going to be able to get from this battery? Notice there are different batteries, right? And so you have like a 9-volt battery, then you only get 9 volts of energy, and so forth. So we looked at copper in our example, and we looked at zinc in our example. Now if you were to look at the table, you will notice that copper, and you have to make sure you're looking at the correct equation, because it does change based on your ion. This is copper plus 2 ion, not just copper plus 1. It would be a different voltage. Same thing to zinc. Make sure you're looking at the correct one. These are all reduction potentials. So if you look at the equations, they're all showing you reduction, the gain of the electron to make something. Over here to the right, it shows you your voltage. This is what you need to know. So as you move further up, you are decreasing the possibility of it being oxidized. As you move down, you are decreasing the possibility of it being reduced. So the smaller the number, the more likely for it to be the oxidized. So looking here, so as you move up, the larger the number. As you move down, the smaller the number. Comparing these two values, negative 0.76 is smaller than positive 0.34. So this is more likely to be oxidized because it has a smaller voltage. And so I would then show this. I'm going to flip it. So zinc, instead of it being reduced, is going to be oxidized and form zinc plus 2 ion, releasing 2 electrons. So I would change my voltage from not a negative 0.76, but to a positive 0.76 voltage. And this is how I know, and I'm going to keep this reaction the same and that voltage the same. Because this is the smaller value, this is the one that now is going to be the oxidized element. This is the one that will be reduced. I need to flip this equation to show that this is being oxidized, and this will remain the same. That is how you use your table. And so this is almost identical to your table. You could actually see here where the copper is. Oops. Yep, that's the right one. Slightly different number. And also too where the zinc is. So I would compare the two. The lower the number, that is the one that's going to be oxidized. This is the one that I need to flip, and therefore also flip my sign. The last part of this just goes through the different types of batteries that you can make then. So a dry cell battery means that you have a paste inside. Rather than having like a liquid, like an acid or something like that, you instead have a paste. Now because of this construction, you could see the zinc, which is your anode, so you have that here, so you have your zinc. And then towards the center, you're going to find your cathode. And so where the ammonium chloride is, or you could have zinc chloride or manganese oxide paste. All depends on what type of battery you have. But the same rules apply. You're going to have an anode and you're going to have a cathode. The anode is your negative end. That's where the electrons are going to come from, so this is what's being oxidized. Oops. And then the cathode is your positive end, so this is where reduction occurs. So here you're able to see those two reactions. Another example would be an alkaline battery, and those two reactions that you would find. So with an alkaline battery, what happens is you always have a basic paste then. Here the manganese oxide. And so it's all the same conditions as a dry cell, but under basic conditions. You still have zinc being oxidized, and now the manganese oxide is being reduced. And now a mercury battery. These are super tiny. So these are really great for hearing aids or watches or stopwatches. And again, the zinc, and you can see where that is located. So at the anode right in here. The zinc is the reducing agent, and the cathode is your mercury oxide, which is down here. So you have your anode and your cathode. It's just on opposite ends of the battery. But again, the same thing, you're going to have your electrical current move from one side to the other. And then lastly, a lead storage battery. This is like what you see in cars. Here you instead actually have like acid, so battery acid, sulfuric acid, that helps as part of your salt bridge. So you have your anode again, which is your lead, your cathode, which is your lead oxide. It's just a slightly different arrangement, but again the same purpose, to have your electrons flow from the anode to the cathode. So I have taken you through what electrochemistry is. Make sure you are able to draw an electrochemical cell, voltaic cell, galvanic cell, whatever you want to call it. Know the direction of the electrons. Know how we could determine what is being oxidized or reduced. Also know which direction the anions and cations will flow, the purpose of your salt bridge, and why we want the electrons to be flowing through an external wire. Be able to identify your anode and your cathode, which is the negative end and which is the positive end. That really is the goal from this PowerPoint. All right? We will go through more questions in class, as well as go through that animation, which will hopefully spark some more of your questions, so do make sure you write them down. This is Mrs. Ewald signing out, saying happy electrochemistry.